Okay, yes, very nice. No issues na beta, understood everything. So today we go to the new topic, the generation game. Okay, here we are talking about generation of electric power. Okay, here we are talking about generation of electricity. Okay, how can we generate electricity? We use it for all our household chores. How can we generate it? Okay, you can see this in your page. There's a diagram of a station. Okay, this is the diagram of how electricity is generated in a power station. Okay, now we have understood in the previous class the law of conservation of energy. Can you please tell me about law of conservation of energy before we proceed? What was the law of conservation of energy? In short, just in short, you write so that I know that yes, my child has understood. Okay, there it comes. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved. Very nice. Very nice, beta. Okay. So the law of conservation states that the total energy of an isolated system remains constant. Okay, which means if energy is changing from one form to the other, okay, then if it has completely changed, then the energy will be equal to the energy which was supplied. Okay, we cannot create it, we cannot destroy it, we can just change energy from one form to the other. Very nice, you have understood it very nicely. Congratulations. Okay, so here now we are changing energy. So we need a source of energy. Okay, we are here changing some kind of energy. I need an energy source which we can change into electrical energy. So the most commonly used energy source is fossil fuel. Okay, you have also understood what is fossil fuel. Coal, petrol, crude oil, all these are fossil fuels. Okay, and then we have also understood that we can also use nuclear fuels. Okay, when a big nucleus divides into smaller ones, some mass is lost and a lot of energy is generated. Okay, Einstein had given us the famous equation E is equal to mc square. Okay, which means if mass is lost, this mass gets converted into energy, and that is what is being used in generation of electricity in the nuclear fuel plants also. Okay, so now let's have a look at how these resources are changed into electrical power. The basic thing, all of these plants, they have a boiler. This is known as a boiler. Okay, a boiler. What does a boiler do? A boiler is used to boil water, to heat up water. If I boil water, what does it change into? If I boil water, we had done a small experiment also. I mean, we just discussed a small experiment also in the previous class, wherein we had taken some water in a bowl and then we had heated it using natural gas. So if I heat up water, what does it change into? Okay, it changes, very nice, it changes into gaseous form, and that gaseous form of water is known as steam. Okay, it's known as steam. Got it? So now steam, we know that the gaseous state occupies a larger volume, it spreads out. Okay, when we condense things, when we cool things, they condense, which means they become smaller in size. Okay, on the other hand, when I heat them, then they expand. Okay, and when they turn into gas, then they occupies whatever space is available to them. Okay, so in the boiler, you can see that I am using fossil fuels. Okay, here I am using, where's my pen gone? Here I am using fossil fuels, okay, to heat up the water. Fossil fuels are burnt and then they supply the energy to water. Okay, if energy goes to the water molecules, they start moving with greater energy, more randomly, and then they change state. Where they, from a liquid state, they change into a gaseous state like you have said, and they turn into steam. Okay, now this steam is contained in a small container. Okay, so it is under great pressure. It is under great pressure. It wants to push the walls away. Okay, so what we do is we give it a small outlet to escape. This outlet, we let it escape. So what it does, it rushes out of this place with a lot of force. I am sure you must have seen your mother doing cooking in the kitchen, and she many a times uses a pressure cooker, right? And if accidentally we remove the weight of the cooker, the whistle, okay, then what happens? From that small space, a lot of steam escapes, isn't it? The same thing happens here also. Okay, we can do it in our house also. I do the same way. I take some water in a cooker and I don't put the weight or the whistle, okay, and I heat it up. Initially I put the weight so that it starts boiling. When it starts boiling, I remove that whistle or weight, and then what happens? This steam, it rushes out of that place. Now if I place a small rotating fan in front, you will see that that fan is rotating with great speed. It starts rotating. Okay, so that same funda, that small scale, here it is being done on a big scale. So this now is the steam is allowed to escape through this small opening. Okay, so the steam is allowed to escape through the small opening, and now this is a turbine. Okay, something which can rotate around its axis. So you can see that it is being turned anti-clockwise if I look from this side. Okay, so this steam rushes into this turbine and the turbine starts rotating. Okay, now what we do, the steam is let's read what is said. The steam is forced through a large fan. Okay, the steam is forced onto a large fan which is called a turbine, and it makes them go around, it makes them spin. Okay, now the next thing I have attached, there's an axle, okay, a rod which is attached to the fan, and on this rod I have a copper coil wound, okay, which has a magnetic core, and this is known as a generator. You will study about these in detail in your senior classes, maybe in 2 years from now. Okay, we'll study about generators. So this generator also is turned. Since the fan is turning, so it makes this generator also rotate. Okay, it has got large magnets. Okay, it has got large magnets inside, and it has got a massive coil. You can see that this massive coil, I told you there's a massive copper coil, okay, which is made to rotate around a huge magnet, or it could be other way around also. In some generators we make the magnets go around, in some we make the coil go around. Either way, the magnetic flux, that is the magnetic field linked with the coil, should change, and if it changes, we get something which is known as induced current. Okay, we get something which is known as induced current. Okay, and this is how electricity is generated. Understood, beta? Okay, so a moving magnet inside a coil of the wire creates electricity. Okay, this electricity, so I get an induced current. The charge that is getting produced over there, it is flowing, so it is electric current. Got it? And now we supply these electric current to distant places. Okay, we have got transformers, we step them up. Okay, we increase the voltage many times, okay, so that no current is lost. And then we have got the national grid. Okay, once we have stepped up the voltage, we supply it. This is the national grid, you can see that. Okay, what is national grid? National grid is a network of cables which takes electric current to distant places. It is not produced in every city, so in one city they produce it, and through the cables they take it to distant places, they step it up, and then when it has reached your house, now they again have a a transformer, which now steps it down, which means it brings down the voltage. Okay, and then you can use it in your house to run televisions, okay, to run microwaves, anything you want. Got it? I hope you have understood how is electricity generated. Give me a yes. We'll discuss in detail now a generator. Okay, I'll tell you a little more details once you have told me that you have understood whatever we have discussed till now. Okay, very nice. So now that you have understood all this, I'll just ask you a few questions and then we move on to the next topic. So my first question to you, the one given at the bottom of your books page, is where is electricity generated? You know that? Very simple. Yeah, we are answering those. We are answering those. Where is electricity generated? You tell me, and then I tell you. In case it's wrong, I give you the correct answer. If it's right, I just clap my hands and say, wow, Rishika has understood everything. So tell me, where is electricity generated? Correct answer. Very nice. Okay. So it's there in the first place itself. Okay. Electricity is generated in power stations. Okay. The next question now I'll answer. Okay. How does a generator work? Okay. In a generator has a huge coil. Okay. It has got a massive coil. What is a coil? Coil is a wound wire, a copper wire which is wound in circular form. Okay, you said something. They do this by capturing the power of motion and turning into electrical energy by forcing electrons from the external source through an external circuit. The last part, by forcing electrons. Okay, I'll give you the last part. Is not very convincing, I'll tell you. Okay, so they have massive coils, and inside they have a magnet. Okay, inside they have a magnet. Now this magnet is attached to the axle of the turbine. Okay, so now the turbine is made to rotate. Okay, and when the axle rotates, the magnet inside the coil also rotates. Okay, thus the magnetic field which is linked to the coil changes. Okay, and induced current is produced. Okay, you learned it this year itself. But the last part, by forcing electrons from the external source. The first part is absolutely correct. They do this by capturing the power of motion and turning it into electric energy. That's what I'm telling you. The motion of the turbine is captured by the coil and electrical energy. Electrical current is generated. That's perfect. Okay, this current is known as induced current. And the second part, I am not very convinced about it. By forcing electrons from the external source through an electrical circuit. Okay, once electrons are generated, they start flowing from this higher potential to lower potential to higher potential. Got it? The electrons start flowing the other way. We take the current to be flowing from higher potential, the positive to this. So we'll take it, chalo. But have you understood what does that mean? Okay, so please understand. I'm happy that you have learned it. Okay, you should understand it also. Okay, so now your answer says by capturing the power of motion. Okay, so the power of motion, this is the power of motion. From where is it coming? It is coming from the turbine. What kind of energy is this, Rishika? The turbine rotating. What form of energy is this? What kind of energy is this, beta? A rotating turbine is What form of energy? We are talking about conservation of energy, okay? So that's why I'm asking you what kind of energy is this. Then we'll get to know that which energy gets changed into electrical energy. No? Should I give it to you? Okay. I just made an arrow. Okay. It's behind my video. I'm so sorry. I'm so sorry. It's behind my video. I understood. Okay. I draw it on top. Okay. I draw it on top over here. I draw it on top like this. And this is the rotating turbine. Okay. So the turbine is rotating like this. The turbine is rotating like this. And the axle attached to it is making the magnet also rotate. So I asked you that what is the energy possessed by this rotating turbine. Okay, so I'll give it to you now. This energy is called kinetic energy. Energy possessed by virtue of its motion is known as kinetic energy. Okay, so this is kinetic energy, the energy of motion, like you have written in your answer also. You have said that by capturing the power of motion. Okay, so by capturing the energy of motion, and that energy which is because of motion is known as kinetic energy. Clear, beta? So now we are turning this kinetic energy into electrical energy. We are turning this kinetic energy into electrical energy. The kinetic energy of the turbine is transferred, okay, to the magnet, and the magnet also rotates in the same direction. The magnet also rotates in the same direction. Now the magnet produces field lines, magnetic field lines, which were getting linked to this coil over here. Okay, so now when it starts rotating, the lines, which magnetic lines which were linked to the coil, are changing, right? And hence current is being produced. Very nice, clear. So this is done. So we take you now to the next page. Okay, we take you now to the next page. Okay, now we go to efficiency and harmful effects of thermal power plants. Most of the countries use thermal power, are dependent on thermal power plants for their electric supply. Okay, tell me about your country. Do you have some idea which is the biggest power plant in your country? Which place is it situated, and what is its capacity? Anything? You can just share the knowledge with me. It'll enhance my knowledge also. I'll get to know a little about the country you're currently living in. Okay, till then I'll tell you that let's look into the efficiency of a fossil fuel power station, okay, or a thermal power station. Okay, and what do they use? They are coal fired. Okay, coal is brought to these power stations in big wagons, big trains. Okay, trains from coal fields collect the coal and carry it to these power stations. Okay, and now this coal, we say, is only 35% efficient. This coal power station is only 35% efficient. So my next question to you is, we have already understood this, okay, in the previous class. So my next question to you is that how much of the energy, ye kahan se laya? Okay, so my question to you is, how much of the energy is wasted in a coal fired power station? My next question to you is, how much of the energy is wasted, what percent of energy is wasted in a coal fired power station? Okay, the Grand Pabura Dam is a gravity dam on the Ogue River, about 15 kilometers south of Franceville in Gabon. Okay, very nice. So the Grand Pobura Dam. See, you are adding to my knowledge. I'll take a screenshot of this, otherwise I'll forget. Just a minute, huh? Let me take a screenshot so that I remember what Rishika taught me today. Okay. And the primary purpose of the dam is hydroelectric power generation. It supports a 160 megawatt. Wow, you have good knowledge. Okay, 160 megawatt, which is 210,000 horsepower power station. That's a massive power station, isn't it? So it must be taking care of most of the electrical needs of the surrounding area. Nice. Thank you very much for the information. See, I am also learning from you. Nice. And 65% is the correct answer. Very nice. If it is only 35% efficient, which means that 65% of the energy which was stored in the coal. Now, you have also understood coal contains which energy? Coal contains which form of energy? Coal is a fossil fuel. Which form of energy is there in coal? Taking long this time. Shall we continue? I'll tell you, okay? Coal, it's written also over there, you can see. Coal contains chemical energy. Here it's written in the second line. Coal contains chemical energy. So what energy transformation are we seeing in this? In this, chemical energy is getting changed into electrical energy. She right. Coal is a combustible black or brownish black sedimentary rock with a high amount of carbon. Okay, I wanted to know what kind of energy it has. So it's there on your book itself, the second line. Okay, I just underlined it, you can see it. It's chemical energy. Okay, so coal contains chemical energy, and this chemical energy gets converted into electrical energy. So if I have 100 joules of chemical energy in coal, which means that only 35 joules of electrical energy will be available to me. Okay, which means almost like you have already stated, 65% of the chemical energy is wasted. It is not converted into electrical energy. Okay, some power stations, instead of using coal, they use natural gas, which again is a form of fossil fuel. Okay, and these are slightly more efficient than these. They are 50% efficient. Okay, so better than this. Here almost 65% of the chemical energy is wasted, and there half is wasted, which is less than this, which means they are much more efficient. Okay, so we again have a Sankey diagram representing this information. We had drawn it last time. Okay, so you know now how to draw them. It's 65, so I draw this. Okay, and then I divide it into half. This becomes 50-50. Okay, then I divide 50 into almost 3 equal parts, so it comes here. Okay, so from here I bring it up to this place, and then I bring my curve like this. It's going into the air, it's getting wasted. Okay, and the rest I carry forward, and again I make a arrow. Okay, so this represents 35 joules. Okay, which is the electrical energy that we have received, one which is beneficial for us, and this represents 65 joules, the energy that has been wasted. Okay, that is of no use to us. During conversion, this chemical energy got wasted, and the total was 100 joules. The total whole thing was 100 joules of chemical energy. Understood better how to draw this Sankey diagram? We had discussed it in the previous class also. So no doubt in this. Understood? Tell me. We have understood that coal fired power stations are not very efficient. they are only 35% efficient, which means, like you said, 65% of the energy is wasted. So what is the energy transformation which is taking place in a coal-fired power station? The energy transformation is from chemical energy to electrical energy. If I have to draw a Sankey diagram, I divided it into two parts. One which has showing a greater portion, 65%. That one is showing that almost 65 joules of energy is wasted, and the other showing me that the 35 joules of energy gets converted into useful electrical energy. Okay, so now that you have understood, I erase all this and I take you to the next part. The next part, an ordinary gas fire. Okay, an ordinary gas fire is 45% efficient. Okay, this we had studied last time. Why is it only 45% efficient? Because some of its energy is lost in heating the air around it. Okay, and some of its energy is lost in heating the container in which it was. Okay, so let's read it out. Because some of the heat escapes through the chimney. How does it escape through the chimney? The air that is surrounding gets heated up. When the air gets heated up, it rises and goes out of the chimney, and the cold air in the surrounding area takes its place, and the process continues. Now this cold air also is heated, and it again escapes out of the chimney. Okay, so almost 65% of, no, not 65, sorry, 55. Okay, so let me erase this. Okay, so now 55% of the natural gas is wasted in losing energy in heating up the air surrounding it, which goes out of the chimney. Okay, now you are supposed to draw a Sankey diagram to represent the energy transfer in a gas fire. Okay, how do we do it? We again make a rectangular piece, okay, like this. Then we divide it into two equal portions. We make a small mark. So this is 50, this is 50, okay, and then 1/10 of this. So this becomes 55. Okay, so this becomes 55. Now I turn it, I take the curve up like this, okay, which means this energy is wasted, and I bring this one forward like this. Got it? So now this represents 55%. This represents 55% energy that goes out of chimney. Okay, wasted. This is wasted through chimney. Got it? So this represents 55% that is wasted through chimney, and here I have 45%. Okay, this 45% is converted into useful heat energy. This is converted into useful heat energy, which is transferred to whatever we have kept on this gas fire to get heated. Clear, beta? Rishika, understood the Sankey diagram for situation number 3, ordinary gas fire. You must be using colors also to make these diagrams in your notebook. Do you use colors? Okay, yes. Now the fourth situation. Okay, the fourth situation, now they say that electric fires are 100% efficient. Okay, I'll change the color of my pen and let me make it some other color. Okay, I use blue. I make it over here. So now I have to draw a Sankey diagram. So I use this, okay, and 100%. There's no wastage. 100%, okay, 100%. Electric fire is 100% efficient. So I have electric fire, which means I'm using a heater. Okay, I'm using a heater which I have plugged into my power point, and it is 100% efficient, which means as much electricity passes through it, that much heat is generated. If I, for an example, if 100 joules of electrical energy is supplied to the electric heater, it gives me 100 joules of heat energy. So it is 100% efficient. If I draw a Sankey diagram, I get a straight arrow giving me 100% conversion from electrical energy to heat energy. So a friend of mine, he says that this means that we should not use gas fires and we should only be using electrical fires. But I know that whatever he is saying is wrong. His logic is that electric fire is 100% efficient as compared to natural gas, which is 45% efficient. But I still say no, he is wrong. How is he wrong? How is he wrong? Why do I say that my friend is wrong? He says that electrical energy, electrical fire is 100% efficient. So we should always be using electrical energy instead of gas fire. But I believe that he is wrong. How is he wrong? Waiting for your answer, Rishika. Even if you don't know, you say I'm not able to. I don't know. That's what I wanted. Okay. See, beta. Now, if I look into the efficiency of electrical fire, it says it is 100% efficient. So sounds very good, isn't it? Here, wow. Whatever energy was supplied to it, the same amount of heat has been generated. No wastage. 100% efficiency. Okay. But when you go into the details, from where have we got electrical energy? We got electrical energy from a coal-fired electrical plant, which is only 35% efficient. Okay, this power plant is only 35% efficient. Okay, and then I lose some energy while transferring the electrical energy from the power station through the national grid also. Okay, so which means that the efficiency there actually is lesser. Natural gas is giving me 45 efficiency. Okay, there the coal powered power station is only 35% efficient, and I say chalo another 2%, 3% is lost. So it comes down to 33%. Okay, which means the overall efficiency, if I look into the details from where this was generated, then it is much lower. Got it? And then the hazards associated with it. I was listening to you when your chemistry teacher was teaching you acid rain and global warming. We also had discussed global warming in the first class. Okay, so if I am using more fossil fuel, I am generating more carbon dioxide. I am contributing to more global warming. Okay, and I am contributing to more chances of acid rain. Got it? Understood, beta? So, using natural gas directly is much better. Its efficiency also is better, and of course, the damage which will be done to the environment also is lesser. Clear? Rishika. Okay, so electric fire is actually coming from a coal-fired power station, because I told you that most of the power stations in most of the countries, they are thermal power stations, which means coal-fired. Okay, the next line says that nearly 3/4 of electricity generated in UK is fossil fueled. Okay, which means almost 75%, 3/4. Okay, 3/4, 3/4 of the electricity which is generated in UK is fossil fueled. So, which means that those power stations we know are less efficient, and then the problems associated with them also are greater. They discuss it in the next line. Okay, burning fossil fuel produces carbon dioxide. You were studying this in the previous class also. I was sitting in the other room and I was listening, right? So if I burn fossil fuel means a hydrocarbon, a compound which is made up of carbon and hydrogen primarily. Okay, so those are hydrocarbons, and when I burn them, it leads to oxidation of the carbon in them, and the oxidation, if it's complete oxidation, I get carbon dioxide. If it is incomplete oxidation, I get carbon monoxide. Got it? And what do? They cause global warming. So now global warming has been discussed by me also in the first class, the very first class which I had taken. I had discussed with you global warming, and I was listening in the previous class. Your teacher also was discussing somewhat acid rain and global warming. So now let us revise. Now you have to write to me what is global warming in short. Make it very crisp. Okay, in the meantime I keep on talking to you. You'll be typing and I keep on talking to you. How are the classes going? How do they conduct classes in your schools these days? Is the situation same there also? You people are locked down in your houses and studying online, or is there some other provision, or are the classes put on hold for the moment? What is it? First you have to write about global warming, other things later. First you answer my question. What is global warming? So it's a repetition of, these points are a repetition of your previous class, the chemistry class. Common things. Of course, science is linked. So it was there also, it is here also. Okay, there comes your answer. Global warming is the ongoing rise of the average temperature of the Earth's climate system. Very nice. It is the ongoing rise of the average temperature of the Earth, because of which the ice caps are melting. Okay, the forest fires are more abundant now. So there are many issues. Okay, and so the carbon dioxide produced by these fossil fuels, since almost 3/4 of UK's power generation is by these coal powered, so there's a lot of emission of these carbon dioxide, carbon monoxide, leading to rise in temperature, leading to global warming. Then these also produce sulfur dioxide. Okay, SO2 is also produced by burning coal, and this can cause acid rains. Okay, in the previous class I was listening, ma'am was telling you that sulfur dioxide, when it combines with the moisture in the air, it leads to formation of sulfuric acid, H2SO4. Okay, so now this sulfuric acid pours on the vegetation on the earth, and does damage. The leaves are damaged, the vegetation is damaged. And of course, when it pours on buildings, whether they are metallic buildings or whether they are marble buildings, both are damaged. Okay, it corrodes the metals also, and it corrodes marble also. So acid, and then it makes the soil also acidic. So if I want to grow something, now it doesn't grow easily, because if I put a seed into the soil, the acidic soil destroys the seed, it doesn't germinate. Okay, so it leads to a good number of problems. This burning of fossil fuel, coal fired power stations, they lead to a lot of problems. Okay, so what option do I have? If I don't want to burn this fossil fuel, how can I generate electricity? Okay, I can use nuclear power stations. Okay, I can use nuclear power stations, which uses radioactive substances. Okay, which uses radioactive substances which have, like uranium, which has huge nucleus, okay, and are unstable, so they can easily break down into smaller nucleuses, and which means they form something else. Okay, so now when they break down into elements having smaller nuclear sizes, then some mass is lost. Okay, and as per Einstein's equation, E is equal to mc square, where m is the mass, c is the speed of light. Okay, as per this, whatever mass is lost, that gets converted into energy, and I can use this energy now. That's heat energy. Okay, now this heat energy is used to heat here. Instead of in this diagram, instead of using now fossil fuel, I am using nuclear energy. That is the only difference. Okay, so now what are the advantages? See, nuclear energy, I will be needing very small amount of the radioactive substance. Here I have to bring tons of coal every day. It is said that almost 800-900 trains bring coal to the biggest power station in UK every day. 800 trains bringing coal, and it gets used up every day. Okay, so that's huge amount of coal that comes to these coal fueled power stations. On the other hand, it would have been a radioactive substance. Okay, for nuclear power, it would not require that much amount. I will not have to transport such great quantity. A small amount can suffice. Okay, what is the disadvantage? Okay, the disadvantage is that the radiations that come out of these radioactive substances, they can do a lot of damage to us. They can cause cancer. They can even harm our DNA. Okay, which means the future generations also are affected. If I am exposed to these radiations constantly, then my babies may be deformed because my DNA has been destroyed, has been damaged. Got it? So these nuclear power stations have this disadvantage, that the radiations can do a lot of harm. They can cause cancer. They can also cause harm to the future generations also. Got it? And what is the other advantage? The other advantage is that they do not produce carbon dioxide. Okay, but one disadvantage gone, the other bigger one has come. Okay, they do not produce carbon dioxide, so now they are not contributing to global warming. Okay, and the final problem which a nuclear power plant has is that building it is very costly. They cost a lot. Cost a lot. Okay, as compared to a thermal power stations, they are almost 100 times costlier. Okay, it has to be built with concrete, it has to be lined with lead so that the radiations which escape don't go into the neighborhood. So they are very costly to build. Okay, the cost of building a nuclear power station is huge. And then I've already talked about the dangerous side effects. Okay, and they produce dangerous radioactive radiations. Okay, not substances, they produce radioactive radiations. These radioactive radiations can cause cancer, they can deform our genetic material, okay. And then once I have used it, then the leftover nuclear material, how do I dispose it? I cannot throw it in the open because it continues to radiate those radiations. So what I have to do is I have to dig deep pits, and then I put them in lead boxes, and then I bury them, okay. And if somebody accidentally digs them out, then again a lot of damage is done. So the dangers are always there, okay. And when I said that they are very little, I can bring them in a box. If 800 trains are bringing coal to the biggest power station in Britain, okay, equivalent to that, I can bring in a suitcase this radioactive substance, nuclear substance. One suitcase will suffice what 800 trains bring, okay. It's equivalent to that much energy, that much coal. Got it? I can bring it in a suitcase and it will produce that much power what 800 trains, the coal brought by 800 trains. Got it? So it is efficient. But how do I bring it? Okay, we cannot carry it openly. So again, bringing it and then storing it, I have to make special places which can block the radiations which are coming out of these radioactive substances. Otherwise, people who are working there, they'll get exposed and their health will be affected. It's very dangerous. Okay, so storing these radioactive substances also is a big problem. What other alternative do I have? People say go natural, okay, go natural. So I can go to biofuels, okay. What are biofuels? One which have come from living things like wood, okay, natural gas, gobar gas, okay, but they are not very efficient. The problem associated with them is that their efficiency is much lower, okay, which means I'll have to use again huge amount of these biofuels. And then again, if I use wood can lead to problems like deforestation. Got it? Understood, beta? Now I'll wait for your feedback. That almost finishes this. We have got one more slide here. We've got quite a lot at present. So we'll be doing this now in the next class. I'll take you there. First, let me ask you whether you have understood whatever I discussed, because you will be getting questions related to this in the next to next page of your book. So if you have understood all this very nicely, then we move forward. The problems associated with nuclear power plants, the problems associated with coal-fired power plants, okay, have you understood them? And then biofuels. Okay, very nice. You have understood. Nice. Today the lag is very little. Okay, so we take you forward. Now, you just gave me some information about a dam, isn't it? And that was the Grand Poubara Dam. Okay, which is a gravity dam. So next we go into that. You'll get to understand how things function in Poubara Dam. Okay. No, that is the hydroelectricity is further. Okay. At present, we can use the kinetic energy. Now, you must have seen that near seashores, the velocity of wind is quite high. Okay. Then in some open areas, desert areas also, the wind blows at a very fierce velocity, a very fierce speed. Okay. So, I told you anything that is moving has kinetic energy in it. Okay, and I know that I can change one form of energy into other form. So I convert this kinetic energy into electrical energy. How can I do that? By using windmills. Okay, the kinetic energy stored in wind can be turned using wind turbines or windmills. everything else is same. The turbine rotates, its axle rotates, the magnet rotates, and in the huge massive coil, electricity is produced. Okay, so instead of now using steam, to rotate the turbine, I am using a wind turbine which has got huge fans, and when wind blows, the fan turns and rotates the generator. Correct? Now the other form, the dam one. Okay, no, just a minute before that we have it. It is caused by waves or tides. We can use the tides also to rotate these turbines. So now moving water also can make the turbine rotate, and I change it into electricity. Okay, now we go to hydroelectricity. Hydro means water. Hydro means water. Okay, so electricity generated out of water by using water, by the flow of water, is known as hydroelectricity. Very simple. If I use the flow of water to generate electricity, it's known as hydroelectricity. Electricity generated out of water. How do I do it? Okay, when water is stored in a reservoir, okay, now I have a hilly area. I'll draw the diagram this side. Okay, now I have got a hilly area. Okay, and at a high altitude, suppose a river was flowing down like this, I build up a wall or a dam in front of it, so that the water which was coming down now starts collecting over there. Okay, so now no water is coming down. Earlier it was flowing down over here, but now I have collected over there. Okay, so now you can see that this is lower level and that is higher level. Okay, so I had told you about energy because of position. Energy because of position. What is that energy called? This is at a lower gravitational potential and this is at a higher gravitational potential. Okay, you had written in your information also that you had sent to me, the Grand Paubara Dam is a gravity dam. Okay, so what does it use? It uses the gravitational potential. Okay, which river's flow is blocked over there? Ogue River. Ogue River's flow is stopped over there. Okay, so the water of the Ogue River which used to flow down, now it is collected in a reservoir. Okay, and then it is allowed to come out through a small outlet. Now if you fill up a big tank and then make a small hole at the bottom, what happens? Water from that small hole gushes out with a lot of pressure, isn't it? So similarly, when I have made a reservoir and I now let water out of a small place, it rushes out. I place my turbine in its path and the rushing water rotates my turbine, it spins my turbine and electricity is generated. Understood, beta? Is allowed to flow down to a power station, it makes the turbine spin. I've told you all this. Okay, so now this is collected in a reservoir and when it is allowed to escape through a narrow outlet, it rushes out. I place a turbine in its path, the turbine spins and electricity is generated. Clear, beta? Tell me, it's almost time, 1 minute up. So we finish it here only, okay? And we'll continue from here. I hope you have understood everything. We'll continue from here, and once we have finished, then we will. I know it's time. You must also be tired, Anna. Before me, you have written it is time. Okay, so that's it for the day. Thank you very much. I hope you have understood, you enjoyed it. Okay, give me your feedback. In case your school gives you some notes or some study material, you can always pass that on to my WhatsApp so that I can prepare my lessons according to that. Right? Thank you very much. Bye-bye. See you.